Welcome back to the deep dive. Today, we're tackling something really ambitious. It's called the SKA Framework,
Yeah, ambitious is right. Because this isn't just, another take on AI or biology. It's making this huge claim
which is?
that physics, how our minds work, cognition and AI, they aren't really separate fields at all.
Okay, wait. So you're saying they're like three sides of the same coin, governed by the same actual laws of nature.
Exactly. That's the core idea.
Right. That's massive. So our mission today, for you listening, is to give you a kind of shortcut, a way to quickly grasp this framework that's trying to unify these, well, enormous fields.
Precisely. Because usually we think about AI as, clever engineering,
Yeah.
smart algorithms finding patterns.
Yeah, lots of code and data.
But SKA says, nope, that's not the fundamental picture.
It rejects that intelligence is just smart coding. So what's the alternative view then? How does it frame it?
Well, the big conceptual shift is this. Intelligence isn't some mystery we just stumbled upon. And it's not just about optimizing things through engineering. It's presented as a law-governed natural process, just like, gravity or thermodynamics, something fundamental.
A natural process governed by law. Okay, so what's the absolute core principle if you had to boil it down to one thing?
The fundamental claim is this. Intelligence is the physical reduction of entropy along a probabilistic path.
Whoa, okay. Physical reduction of entropy
Hmm.
along a probabilistic path. That ties thinking directly to physics, like thermodynamics almost.
It does. It treats thinking, learning, deciding as a physical system that's always trying to find the most efficient way forward, but in terms of information.
Fascinating. Okay, that tees up the first law perfectly, doesn't it? Law 1, the law of probabilistic decision-making. Let's call it D.
Right. So D is about the baseline ability of anything intelligent, human, AI, whatever, to make a choice when things are uncertain.
And the key is uncertainty, right? It's not deterministic.
Exactly. Intelligence, according to this, is never deterministic. There's no simple on-off switch, no binary yes or no when you decide something.
It's more like a calculated bet.
A calculated bet, a weighted guess,
Yeah.
based on absolutely everything the system knows up to that moment.
A weighted guess feels like a continuous thing, not a sudden flip. Is there a formula for that?
There is, and it's surprisingly elegant, really. Just D equals sigma of Z.
Okay, let's break that down. D is the decision probability.
Yep, your confidence level. Always a number between 0 and 1. 0 means no confidence, 1 means total confidence.
And Z. That's the input. You said accumulated knowledge, but what does that actually mean in this context? Is it just memories?
That's a really good point. It's more formal than just memories.
Yeah.
Z represents the system's entire current informational state. Think of it like a huge vector capturing everything relevant.
So sensory input.
Sensory input, yes, but also learned associations, memories, internal models, the whole shebang, everything relevant right up to the instant of decision. It could be, incredibly high dimensional.
Okay, so you have this potentially massive, complex state, Z, and it somehow gets mapped to this simple 0 to 1 confidence level, D.
Yeah.
How does that happen? What's the sigma doing there?
Sigma is the key. That's the sigmoid function. It's the mathematical bridge.
A bridge.
Yeah, because Z can be this sprawling, messy sum of all sorts of information, positive and negative influences.
Yeah.
The sigmoid function takes that potentially huge, unbounded value.
It squishes it.
Exactly. It elegantly, smoothly squishes it down, normalizes it into that neat probability D that has to live between 0 and 1.
So no matter how wildly the input Z might vary based on new information, the sigmoid ensures the output D is always a sensible probability, a confidence level.
Precisely. And it shows how that confidence isn't static.
Yeah.
As your Z, your internal knowledge state changes, even subtly, your D, your decision likelihood, adjusts smoothly and continuously. It's not a switch. It's more like a dimmer dial.
That makes intuitive sense. Like, think about wondering if you turned off the coffee maker. Your brain isn't doing a simple check, yes or no. It's adding up fragments, right? The visual memory, maybe the lack of a coffee smell, the memory of being rushed.
All those fragments make up Z.
And that sum gets mapped via sigma onto your feeling of confidence, D, which might fluctuate as you think about it more.
That's a perfect illustration. It connects the internal state directly to the decision probability. Okay, so if decisions depend on our knowledge, Z, the obvious next question is, how does Z grow? How do we learn?
Which brings us to Law 2, the Law of Knowledge Accumulation, or H.
Exactly.
So how does SKA define learning, especially if it's all grounded in physics?
Right. This is where information theory really comes in. The core principle here is that knowledge only grows forward.
Forward only.
Forward only. And it happens specifically by reducing uncertainty And in physics terms, reducing uncertainty, well, that's reducing entropy, H.
So learning isn't just collecting facts like stamps.
Yeah.
It's an active process of making the world, or your internal model of it, less random, more structured, more predictable.
Precisely. Learning is the reduction of entropy. Structured accumulation is entropy reduction.
Okay, let's use an analogy. You mentioned learning to drive stick shift earlier.
Yeah, perfect example. When you first start,
Total chaos, high uncertainty, high entropy. You have no idea what you're doing.
absolutely. The entropy is huge.
Yeah.
You don't know the clutch point, the timing, why it's stalling. But then every time you get a smooth shift or figure out why it stalled and fix
You're reducing the chaos, reducing the
it's
uncertainty.
used to H, the
Oh,
entropy.
yes.
And simultaneously, you're building structured knowledge, Z. The whole system of U plus car becomes more ordered, more predictable.
So Z goes up as H goes down. That relationship is central. Okay, but here's the big one, especially for anyone working in AI today. The framework seems to explicitly reject the main tool we use for learning in machines.
You mean gradient descent, backpropagation.
Exactly. Backprop is the workhorse. It's how almost all deep learning happens. How does SK justify throwing that out?
Yeah, this is probably the most controversial or radical part from an engineering perspective. Gradient descent, backprop. It works by backward error correction.
Right. You run the data forward, see how wrong the output was, calculate an error signal.
And then you propagate that error signal backward through the network, layer by layer, adjusting the connections, the weights, to minimize that specific error. It's fundamentally retrospective.
Looking back to fix the mistake.
Exactly. SKA proposes something completely different. It calls it structured refinement, and crucially, it's forward-only.
Forward-only refinement. What does that mean in practice? How does it get better?
The theoretical leap is significant. Instead of calculating errors and derivatives backward to fix past mistakes, SKA suggests the system, by its very nature, selects the next informational step or state transition that inherently minimizes future uncertainty.
So the focus shifts entirely. It's not about fixing the error you just made, but about intrinsically building a better, more ordered, lower entropy state from the get-go.
That's the idea. It's optimizing the path forward based on reducing potential future entropy rather than correcting past prediction errors.
Which, if it works, could also avoid the huge computational cost of backpropagation, right? Those backward passes are expensive.
Potentially, yes. It argues for a process that might be more aligned with how physical systems naturally evolve, seeking efficiency, and may be more computationally tractable in the long run because you skip that whole backward pass.
Okay, so this forward-only drive towards reducing uncertainty, reducing entropy, that needs a guiding principle. How does it know which path reduces entropy the most?
That leads us straight to the third law, the real physics anchor. Law 3, the law of entropic least action, or L.
Least action. Okay, that rings a bell from physics class, like light taking the fastest path, or planets orbiting along efficient trajectories.
Exactly. The classical principle of least action says physical systems tend to follow paths that minimize action, which is usually related to minimizing energy expenditure over time. Nature is, in a sense, lazy or efficient.
So how does SKA adapt that? What's the twist?
The twist is simple, but profound. SKA substitutes entropy for energy or action.
Okay, so intelligence, when faced with all the possible ways it could learn or think something through.
It naturally, or physically, follows the path of least entropy, the route that requires the minimum informational effort, the one that wastes the least information, the one that reduces uncertainty most efficiently.
So if you're learning, say, quantum mechanics, your mind isn't just randomly grabbing concepts. It's subconsciously trying to find the sequence of ideas, the conceptual path that makes the whole subject click with the least amount of wasted mental effort or confusion.
That's the claim. It's like your cognitive system has an internal compass needle that's always trying to point toward the direction of steepest entropy descent. It's seeking the most efficient learning trajectory.
An internal GPS for learning. I like that. But mechanically, how does it work? The framework talks about an entropic Lagrangian, which sounds complicated.
It does sound heavy, but the concept parallels classical mechanics. A regular Lagrangian, in physics, helps you find the path of least action by looking at the difference between kinetic energy, energy of motion, and potential energy, stored energy.
Right, and minimizing that difference over time gives you the actual physical path.
Exactly. So the entropic Lagrangian, L, does something analogous, but for information. It measures the dynamics, the interplay between how fast knowledge or structure is growing.
Like informational kinetic energy.
Sorta, yeah.
Yeah.
and the resistance it's working against, which is the uncertainty or entropy.
Like informational potential energy.
You could think of it that way. It's quantifying the trade-off between gaining structure and the cost in terms of remaining uncertainty or informational effort.
And then by applying the same mathematical machinery, the Euler-Lagrange equation, to this entropic measure.
The system automatically finds the path that minimizes the informational cost, the path of least entropic action. It intrinsically optimizes for informational efficiency.
So cognition, in this view, literally evolves like a physical system following a variational principle, but it's minimizing informational cost, not energy cost.
That's the core synthesis. It aims to put thinking on the same fundamental footing as other physical processes.
Okay, this ties it all together nicely, but let's circle back to that really tricky point. If SKA throws out backpropagation, the main way AI currently learns from errors, how does an SKA system even know it made a mistake? How does it improve if it's not correcting errors?
Right, that's the crucial conceptual hurdle. SKA's answer is that improvement isn't reactive correction. It's what they call intrinsic course optimization.
Intrinsic course optimization.
Meaning in a traditional AI, you make a decision, you get feedback, nope, that was wrong. That's the error signal, and you adjust backward based on that signal. In the SKA model, the system is always, at every moment, being drawn towards states of lower entropy, guided by Law 3, least entropic action. A mistake isn't flagged by an external error signal. It's simply recognized intrinsically as being in a suboptimal informational state, a state with higher than necessary entropy.
Ah, so a mistake is just a high entropy location on the informational map.
You could say that.
Yeah.
And the system's fundamental physics, Law 3, automatically compels it to move forward towards the next state that most efficiently reduces that entropy, regardless of whether the previous state was labeled a mistake.
So the correction is built into the forward movement itself. It's constantly seeking the most efficient path downhill on the entropy landscape.
Exactly. The optimization is inherent in the dynamics, dictated by this physical drive to minimize future informational effort or uncertainty. It's a shift from designing systems that react to errors to, potentially, designing systems that simulate this natural law and are therefore inherently drawn towards efficient, low-entropy solutions.
That is a genuinely fundamental shift in perspective for how we might build AI. Okay, let's recap the 3 laws quickly for everyone listening. Law 1, D.
Probabilistic decisions.
Yeah.
Your choices are weighted bets based on your current knowledge state, Z.
Law 2.
Knowledge accumulation. Learning is forward-only structure building, defined as the process of minimizing entropy, H, or reducing uncertainty.
And Law 3, L.
Entropic least action. Physics guides the learning process along the most efficient path, the one that minimizes informational cost or effort, governed by an entropic Lagrangian.
Okay, so the unified picture here is that intelligence isn't some weird, separate, mystical thing.
Not at all. It's being proposed as a natural physical process, governed by variational principles, much like mechanics or optics, just operating in the realm of information and uncertainty.
Which means the big takeaway, the shortcut phrase for you to hold on to, is moving from saying AI works because it learns patterns
to saying intelligence is the physical reduction of entropy along a probabilistic path.
That really does reframe the entire quest for AGI, doesn't it? Grounds it right back in fundamental physics.
It does. And, if you really push on that idea of entropic least action, that intelligence inherently seeks the most efficient informational path forward.
Yeah, where does that lead? What's the big implication?
Well, it leads to a pretty profound, maybe even unsettling final thought. If intelligence, whether it's ours or artificial, is fundamentally guided by this drive to minimize informational cost, to minimize entropy.
Could we potentially predict its trajectory?
Could we, if we understood its initial state well enough, and these governing entropic laws, ancient L, truly hold, could we, in theory, predict its long-term evolution, its emerging goals, its behavior, even if it becomes vastly complex, simply by understanding its inherent drive toward informational efficiency?
Predicting the future path of intelligence based on its need to minimize informational resistance. That is, wow, that's definitely something to chew on. It absolutely changes the conversation from just clever engineering tricks.
Back to fundamental physics.
Yes. And for anyone whose appetite is whetted for the really deep math behind the entropic Lagrangian and the detailed derivations.
The original papers are out there, usually on platforms like Arcsine. You can definitely dive in.
Fantastic. Well, thank you for guiding us through this really deep dive into what could be the physical laws of intelligence itself.
My pleasure. It's fascinating stuff.
Indeed. Thanks for joining us, everyone. Until next time.